after lunch, and we have a very exciting talk on the power of positivity by Kunal Marwaha with Rusbe and Bill Pfefferman.
Thanks. So my name is Kunal. I'm a graduate student at University of Chicago, and I'll be talking about QMA and QMA plus, what the power of positivity can do for this complexity class. It's a preprint we put out last month with Rusbe and my advisor, Bill. And it's also inspired by a work by Fernando Jeronimo and Wu that appeared in STOC this year. So kind of the outline will be two parts of the talk. First, I'll kind of give an introduction to this QMA plus, this new complexity class, and try to motivate some of the context that led to this. And then I'll walk you through the key steps in the proof. So the context here is really about QMA and QMA2. And the question here revolves around the power of unentangled proofs. So if QMA is our quantum version of NP, QMA2 is kind of this fundamentally quantum thing where the proofs have a special form. So to review, QMA is a set of decision problems that in the yes case, there's some quantum proof that's input to a BQP machine, and you accept with at least probability C. And in the no case, no matter what quantum proof I get, if you input in a BQP machine, it'll accept with at most probability S. This is a standard definition of QMA. QMA2 has a slight wrinkle in this, where it's also a set of decision problems. But in the yes case, you have this state that is separable over, let's say, half the qubits. So the quantum proof is unentangled across this bipartition. But in the no case, and this is actually really important, in the no case, you're only resistant against states, against quantum proofs that are unentangled, also on this bipartition. So in QMA2, a QMA2 protocol might actually get broken if you were allowed to send quantum proofs that were entangled. And so this kind of promised symmetric restrictions actually makes the class much trickier to study. And I'll explain, how that motivates this. So let's talk a little bit about some facts about QMA and QMA2. So the first thing you might ask is, does the C and S matter? So if C and S are at least inverse polynomial apart, you can amplify the gap. And so for QMA, you can do this with parallel repetition. How does this work? You repeat the verifier circuit many times. And in the yes case, you're going to get many copies of the right quantum proof. And in the no case, even though they could be entangled, you can't, cheat. For QMA2, this doesn't actually work, but there's another thing you can do called the product test by Haro Montanaro. And this allows you to amplify the gap in QMA2. So the C and S, once they're inverse polynomial apart, it doesn't seem to matter how big they are. Another thing you might want to know about is upper bounds. So both of these classes can be simulated in NEXP, non-deterministic exponential time. So how can you see this? The BQP machine can be simulated in EXP, and the quantum proof can be guessed non-deterministically. So for QMA, you can do better. You can in fact put it in P space using a semi-definite program. And in fact, even tighter bounds are known, PP and A0 PP. But for QMA2, we actually don't know any other stronger upper bound. And the question is, why can't we do better? Can we do better was the question, I think, for a long time. And now maybe the question is, why can't we do better? Maybe actually this QMA2 is super powerful. Maybe it's equal to NX. Questions so far? So this motivated studies of NP protocols in QMA2 and other things that I think inspired Jeronimo and Wu to define a class called QMA plus. Okay, and let me walk you through the definition of QMA plus. So QMA plus again is a set of decision problems, where in the yes case, my quantum proof has an additional promise where it has to have non-negative amplitudes. So what do I mean here? I mean that take the computational basis, take the state vector, and I mean all the amplitudes are real and non-negative. Okay, and again, in the no case, I'm only going to be resistant against states of this type. So quantum proofs that are non-negative amplitudes. So you can similarly define QMA2 as the same kind of, QMA2 plus as the same kind of setup, where the proofs are unentangled and they have non-negative amplitudes. So now you're kind of asking about the power of this non-negativity.
I guess QMA2 has
Yeah. So the motivation, I'll explain the motivation for why this. So they made this modification to the complexity class that allowed them to prove something, and I'll explain what that is. Okay. Is the definition clear? So you might say, okay, maybe I've seen a class like this before. There's a paper that studies SQMA, QMA with subset states. And here you restrict a subset state is a state that's uniform over some subset of the computational basis states. And you could say, oh, there's this SQMA, which the quantum proof has to be a subset state. But actually, this restriction is only in the completeness. It's only in the yes case. And so it's kind of for this reason that SQMA is equal to QMA. Because in the no case of SQMA, they're resistant against all quantum proofs. Whereas in these kind of other types of complexity classes I've been showing you, the restriction is two-sided. We're only resistant against a certain class of quantum proofs. Yeah?
there we have the optimal witness can be a subspace state.
The optimal witness.
Yeah, for the no case. There's a trick that you add an ancilla. If it's 0, then you accept. It's very too far or something like that. And then there was an optimal quantum witness that, optimal subspace witness that accepts.
Yeah, so, and I'll talk probably, if you have two-sided restrictions,
Okay.
then there is some gap where they're equal. Yeah, but it depends on the gap. Yeah, good. But I think a lesson here that I want to hone in is like, if you have this promised symmetric restriction, you can actually increase the power. You can make the class a lot more powerful because you're kind of restricting Merlin's ability to cheat. Okay, so we might try to ask some of these same questions about QMA plus and QMA2 plus. So we can say, okay, what about gap amplification? Do those CNS parameters matter? And it turns out they might. The standard thing you would do is parallel repetition. You would repeat a verifier circuit many times. And the main thing that breaks down here is, so in the yes case, it works. In the yes case, you can send me many copies. But in the no case, Merlin can kind of use the fact that you're making partial measurements to eventually send you states that have complex phases in them. So kind of like a graphic here is that, if we repeat this verifier circuit many times, we might start with a state with non-negative amplitudes. But if we make a partial measurement, let's say over the first third of the qubits, we may not have a state that has non-negative amplitudes anymore. And this can be, used to kind of get a better score than what you would hope a cheating Merlin would do. Okay, so this what this says is the technique for parallel repetition to get gap amplification just doesn't work. And this, by the way, also happens with QMA2. So it doesn't mean that there's no way to gap amplify, just that this technique, this naive technique, won't work. So the other thing you might try is, maybe we can upper bound this class, okay? And so maybe we can, write down a semi-definite program that optimizes over the best quantum proof. And it turns out this also fails. And the reason this fails is that if you're trying to optimize over states with non-negative amplitudes, this turns into optimizing over the copositive cone. And this, if you have polynomial size matrices, you can compute independence numbers of graphs and so on. These are NP hard. So for exponential size matrices, it's not clear it's any less hard than all of NX. So this technique also can't work to give you an upper bound.
What is a copositive cone?
So copositive cone is sort of the cone you would write down if I want to optimize over the best quantum proof, where all the entries in the proof are non-negative. So I guess it's a name that it found. So when we were looking at the literature on this, we found that this object had been studied before, and they called it the copositive cone.
Has it been studied outside the quantum context?
Yeah, it's been studied outside the quantum context. Yeah.
I mean, what threw me off here in thinking about this is that you can, in polynomial time, optimize over all non-negative density matrices.
Right. And for very, very small system sizes, like size 4, actually they're the same, but this object is slightly different than the copositive cone.
Yeah.
Good. Okay. So do you mind asking me, so how powerful is this plus? What is the plus giving you? And I would like to say that actually, from one lens, the plus is not giving you a lot of power. And what can you say? So this is observed by Jeronimo and Wu. Every state psi has a 1/4 overlap with a state with non-negative amplitudes. Okay, how can I see it? I'll just walk you through it. I take a state, I take its real part and imaginary part. Take the part that's bigger. Let's say it's real. Now take the real state. Now split the positive components and the negative components. Take whichever is bigger. Now I have a state with non-negative amplitudes. It has 1/4 overlap. So what that means is you can turn a QMA plus protocol with a big enough gap into a QMA protocol. And the same thing for QMA2 plus, you can turn it into a QMA2 protocol. So it means that there are these constants, CNS, where QMA plus equals QMA and QMA2 plus equals QMA2. So in some ways, if you choose CNS big enough, these classes are like cousins. There's a QMA class and there's QMA plus. There's QMA2 and there's QMA2 plus.
But you mean if you choose C big enough and S small enough?
Right, yeah. So sorry, if I choose the gap big enough. Thanks. Yep.
So if you choose the gap big enough, you get some gap for QMA, but then are you able to amplify it?
Well, you can amplify QMA.
Can you? But you're saying you can amplify it while keeping those restrictions. So if CNS are different enough, then you can for QMA plus, and as QMA plus you can amplify it.
That's what this also implies. Yeah.
Is it clear that if you have an efficient way of creating your original state, that you can also create actually that state that has 1/4 of overlap with that state efficiently?
Efficiently?
Because you need some kind of a separate.
So I don't know if you need to do it efficiently. So the proof of how you can do this is that if I have a protocol, let's say C is 0.9 and S is 0.1, then I can turn it into a QMA C and 4S protocol. Because now every state that I send through is going, at least 1/4 of the state is going to fail.
So it's not important to be able to create.
No, it's not important. It's just an analysis technique. That's correct. Yeah. It's in fact the same technique that's in the Grillo et al. Paper, the study of subset QMA.
So these C prime and S prime, are they constants here or are they dependent on?
Yes, they're constants. Okay, but what was surprising, and I think this is what motivated this class in the beginning, was actually for QMA2 plus, there are some other constant CNS you can choose that's equal to NX. So what does that mean? So on the one hand, QMA2 plus is equal to QMA2 for some gap. And on the other hand, QMA2 plus is equal to NX for a different gap. And so if only you can add, if this gap doesn't really matter, if you can gap amplify, then actually that would imply that QMA2 equals NX. And I think this was a really exciting result because it gave you a new opportunity to study QMA2. So our work that came out last month kind of says something that complicates the picture. In fact, the same thing is true for QMA plus. There are some constants you can choose, CNS, where QMA plus is equal to NX. And what we do is we take the Jeronimo and Wu proof, we make several modifications, and we show the same thing works even if you only have one copy. So now we have a class, QMA plus, that interpolates, if you change this gap, C minus S, or you take the ratio C over S, that in constants goes from QMA all the way to NX. And QMA is contained in X and even in smaller classes. So unless QMA equals NX, which is extremely unlikely, there's no way you can have gap amplification of QMA plus. So this kind of complicates the picture of gap amplification in this class. So I want to, give one slide on how do you interpret these results. There's kind of QMA and QMA2, and these cousin classes, QMA plus and QMA2 plus. And the first thing you might say is maybe actually all the power is in this plus. The plus is what's giving the power. It's not the 2, it's actually, the plus. But I mean, it's not clear, right? Because, at some constants, it's equal. The classes are equal. And so at least if you're going to use positivity in this QMA2 plus to study QMA2 and NEXP, whatever gap amplification technique you use cannot work for QMA plus. So you're going to have to be a lot more clever about using unentanglement and positivity to get gap amplification, if it exists at all. Questions? Okay. So from here, I'll go through the proof outline. I think we'll have time to go through it. And I'll kind of separate it into two parts. First, I'm going to put NP in QMA plus with a logarithmic size proof. The reason I do this is pedagogical. It's so we can talk about polynomial. Everything is polynomial sized. I don't worry about succinctness. I don't worry about exponentials. That's the main reason. But it turns out everything can scale to NEXP. And I'll say a couple of words about how you do that at the end. Yeah.
Before we proceed, will you tell us which parameters of completeness soundness give you NEXP for QMA plus and QMA?
So I don't know, for QMA plus equals QMA, you can use 0.8, 0.2, or anything above that, 0.81, 0.19. For QMA plus equals NX, I know they're constant. I don't know what the constants are. Yeah. Good question. Okay, so how are we going to start? We're going to have to choose a problem that's NP hard. Okay, so we're going to use the obvious thing. We're going to use a CSP, a constraint satisfaction problem. We'll say there's n variables. We'll say there's a bounded alphabet size, and kind of Q uniform constraints. Q is also bounded. And we'll basically ask is if this instance is fully satisfiable or not. And the first thing we're going to do is we're going to use the PCP theorem, and we're going to say actually we're going to ask a stronger question, which is actually still just NP complete, which is the completeness 1, or sorry, can you satisfy all the constraints, or can you only satisfy half of them? It turns out that this gap, as long as it's constant, doesn't matter. As long as it's constant, the proof goes through.
What's Q?
So Q is like the number of variables that is involved in a constraint. So for maximum cut, it's 2, but for others, it's bigger. Okay. So the plan is to solve this in QMA plus with a logarithmic size proof. So I want to give you kind of a picture here. This helps me understand what positivity is doing. You know, on the left, we have kind of two wave functions that have positive and negative amplitudes. And they can cancel. You know, you kind of are adding these two wave functions and they disappear. Where on the right side, everything is non-negative. And so you can't cancel out amplitudes. And so in a way, like this positivity thing is kind of taking out the destructive interference. It prevents things from canceling out when you might want them to. So it removes a kind of a way that Merlin can cheat. If you know the state has positive non-negative amplitudes, then you can't use it to create destructive interference.
Is that a visible picture?
I'm sorry?
Is that a visible picture? I mean, I apply sigma into the first qubit. Can you repeat the question?
So it was asked, is this a reasonable picture? Because if I change the basis, then this may not be true. So what I'll say is these results hold as long as you can have a basis that you can efficiently get to the computational basis. So if your non-negative amplitudes in some basis that is you can prepare from that basis into the computational basis, then this works. Okay, so what we're going to do is we're going to require Merlin to send a certain type of quantum proof. So we know that the proof is non-negative amplitudes, and we're going to ask basically for a stronger property. And I think the big idea here from Jeronimo and Wu is that if you look at the overlap in a Hadamard basis with the 0th Fourier component, it's actually proportional to the L1 norm of the vector. And so if you have a projector in the Hadamard basis and you look only at that 0th component, then you're going to accept a state with non-negative amplitudes relative to its L1 norm, relative to kind of its measure in this measure. Sorry. And so I will say this is like kind of the only use of positivity in both papers, is like to do this, something at the bottom of all of the positivity constraints is this object. And we're going to use this object in ways to guarantee a stronger kind of state that Merlin is sending us. But this is the kind of the key point.
I mean, I had thought of the key point as being that with non-negative states, if you have two orthogonal ones, then they must have disjoint supports. Is that just a special case of this fact?
Non-negative states.
Yeah, if they're orthogonal, then they have disjoint supports, right? Or at least like when Jeronimo and Wu talked about it, like that was what they presented as the key fact.
Yeah, I would say this is kind of like a special case.
Kind
Yeah,
of the same thing.
Yeah.
Okay.
They have two different parts, and one of them involve that.
Oh, I'm not sure.
I would say underneath all of this is kind of measuring in the Hadamard basis gets you a measure of L1.
Isn't this sort of saying this would give you a a way to show that your superposition is spread out?
Yes, exactly. Yeah.
It is sort of, I think these are dual approaches.
Okay.
So I'll walk you through how Jeronimo and Wu use this assumption, and I'll kind of present the key point, at least from our perspective. Is first notice that QMA 2 plus and QMA K plus are equal with some constant gap. Not all gaps, of course, but for some constants. And you can see this by walking through some of the Harel-Montanaro steps. Not all of the steps work, but some of them do. That gives you this. So you can assume now that you have many copies of a state with non-negative amplitudes. And then what we'll do is we'll project this pi plus operator on each copy, and we'll count the fraction that accepts. And this gives us an estimate of the L1 norm, because this operator accepts proportional to the L1 norm, so it gives us an estimate. And so what we can then do is we can ask for states that are close to an L1 norm that I want. So if Arthur has a particular sparsity in mind, then they can ask for it by making sure the states are close. Okay, and you can use this to get stronger properties like subset states and so on, but this is kind of the main point, is you can estimate the L1 norm. So with one copy of the state, we can't do that, right? With one copy, we can only measure one thing, or at least partially measure. So what we're going to do is something slightly different. We're going to separate the registers into two parts. We'll say the questions, which have log n qubits, or they'll have poly n qubits in the NX protocol, and the answers. And it's very important the answers are only constantly many qubits. Okay. What we'll do is we'll choose one of two tests. We'll choose either a test, the pi plus over the whole input. So we're kind of encouraging the state to be as dense as possible. And the second test we'll choose is kind of the complement of the pi plus operator, but only over the second register. Okay. So this second test, if you had a general state, you can pass it with probability 1. But if you have a state with non-negative amplitudes, you can't actually pass this with probability 1. The reason is you're accepting kind of proportional to the L1 norm, which can't go down beyond kind of just one component in the answer register. Okay. So in the second point, I have some projector, and the projector I can there are states that succeed the projector with probability 1, but if I promise that my state is non-negative amplitudes, then I claim that I cannot pass this with with probability 1.
And the test is checking whether this expectation is high enough.
Yeah, I just measure this. Yeah, I count the probability of acceptance. Yep. So you can say like the second test, what it's doing is it's trying to minimize the number of answers. So for a given question, it doesn't really matter how many questions you have, but for a given question, in the answer register, I only want there to be one answer. If I have two answers, then I'm going to fail with more probability. So choosing tests like this, choosing the probabilities correctly. If I want the state to be as dense as possible, and yet that spread out as possible. And at the same time, I want the state to be have only one answer per question. Gives me states of this form, which I'll call a rigid form. And the form is kind of uniform over the questions and one answer per question. So what we're doing is now we've guaranteed a state of this form. And if you're far away from this form, you're going to fail these tests with a constant bigger than states like this will fail. Okay, so this isn't as general as getting a target L1 norm or something like that, but it turns out this is all you need to finish to kind of finish up the solving the NP problem. Other questions about this?
And you're doing these two tests separately, and you're keeping space to accept.
That's right. So with some probability P1, I do the first, probability P2, I do the second.
But you want to be very, very, very precise on your answers on each one separately.
No, I only need to do it once.
Or is it-
Yeah, because I do it once and then I see the probability I accept. And what I'll see is the maximum probability I'll accept will be states of this form. And if you have,
But don't you then get a trade-off between how spread out and how concentrated?
yeah, so this comes down to the key point is that the answers are only constantly many. So once you have more answers per question, you start failing much more often. So this is, yeah, it's a good point to make sure the trade-off works correctly. But it works kind of, the way we got it to work was kind of only if these answers were constantly sized. So maybe one picture that might help is presented an idea from Brian O'Gorman, which is you have test 1 and test 2, and we're going to look at the kind of the success rate of this test. And so they were orthogonal operators, so you can't pass them. The sum of passing them can't be more than 1. But if you have states that are non-negative amplitudes, it kind of blocks off some amount of passing test 2. And so the rigid states we're looking for are at this circled point. And if we choose the probabilities of test 1 and test 2 appropriately, the best thing you can do is give me states at that circle. So how are we going to use this power? So I'm going to make the questions the constraints. So that's pretty important. I'm going to make the questions constraints. And I'm going to make the answers the assignments of the associated variables. So
solve a 3-set problem or?
Yeah, so we're going to solve some CSP. Let's say it's 3-set. Yeah. So if it's 3-set, then the constraints will have R constraints, some poly-n constraints, and I'll have 3 variable assignments per constraint. Okay. And so in the completeness case, in the yes case, there's going to be some satisfying assignment. So I can always set the variables so that every constraint is satisfied. But it's important, notice that the first register are constraint indexes from 1 to R. And the second register, the answer, is kind of a list of variables. And I might use a variable more than once. In fact, I probably will. And so in the yes case, I can always write down some satisfying assignment. So with some probability, we're going to test this rigid form, using those tests I gave you. And with some other probability, we're going to test the constraints.
What's J here? J is like 1 variable, or there's 3 variables of a constraint, or nothing? Or
So J is the index of the constraint. Let's say I have,
the constraint.
yeah, so let's say I have n variables and R constraints, or R is some poly n.
Okay, so testing for the rigid form means testing both that the superposition is uniform and also that there's exactly, that there are no phases. Well, there couldn't be phases anyway because of the non-negativity.
That's right.
Right? So it's really just like a uniformity test.
That's right. In a way, if you're familiar with these NP protocols, this was the kind of thing is you need some uniform object.
Yeah. And do you need just one copy of psi or multiple copies?
Just one copy. Yeah. So with multiple copies, you can get a measure of sparsity, and you can use that to get subset states, and that gives you that correct form in Jeronimo and Wu. in our approach, those two tests, those kind of pi plus or kind of pi plus over the second register, that gives you this form.
Okay, but with one copy, you get some constant completeness soundness gap, which might be a really, really tiny one.
That's correct.
Okay, and can you get a better one if you have multiple copies of psi?
That's not clear. Not clear. Yeah. So, okay, so how do we test these constraints? So from here, we're going to assume that the states are rigid, because if they weren't rigid, the other parts of my protocol would have found that. And actually, for rigid states, checking the constraints is quite easy. I'll measure in the computational basis, and I'll get out some j and f of j. J is the index of a constraint. F of j are the Q variable values associated with that constraint. And I'll check it. I can compute it classically. Or if you want, I can compute this in superposition, so to speak. But in soundness, Merlin can cheat. I could send, for the same variable on different constraints, I could send different values that make the constraints pass. So we kind of need to add one more test to make sure that the variable assignments are consistent. So this consistency test is kind of the most technical part, but it's also the part that's been done before. But let me describe what this consistency test is about. We're going to try to construct a set of unitaries, let's say constantly many unitaries, such that if you're honest, if you have a consistent assignment, then the state is invariant under the action of the unitary. So psi is equal to u psi.
If you have something naive, such as if you just measure f of j and then make sure that your superposition is consistent with that, would that not that you don't have, f of j is now a variable, is some variable, right? So you make sure that your superposition on the first register doesn't include both, that variable negated as well as unnegated.
So are you suggesting changing the question and answers to be?
No, not
But f of j is a list, right?
I'm sorry?
But f of j is a list, it's not just one thing.
Sorry, I thought f of j was focused on one.
It's one constraint, so that's an important distinction. So if the j is a constraint, f of j is, let's say, q different variable values.
But it was focused on your rigidity.
Only one in superposition, right.
Right. So now
each
if you were to measure f of j, so if I think of it as a superposition over j, so those are the constraints, and then for each one you've picked out exactly one variable, right? That's what the second register is, isn't it?
So it picks out the whole list. So so q is constant, sigma is constant. So I can actually include the whole list of variables, and that can be my answer. So let's say 3 sat over binary instances. There's kind of 8 strings I can send, and I will choose one of the 8 strings to send. And this is important. So I think there are ways to kind of encode just variable and values, but then you have a hard time actually checking that the constraint is satisfied.
So you're saying you actually chose to give an assignment to all the variables in the thing, because you can check it if you just pick one.
Yeah.
And if you just pick one, could you do the test? So wouldn't there be this? So there seems to be this simple test, but maybe it doesn't work, where you just measure the variable name, and now look to see if the superposition of the first register is its support is only on one, on unnegated or unnegated, right? So that would give you a test. Maybe it doesn't work. Maybe it's error probability is too high or something.
No, we only have 3 qubits in the answer register. So that same qubit corresponds to different variables.
Right.
According to that.
Exactly. No, that's what I'm saying. So it, so now, okay, maybe we can.
Yeah, we can take this off. Yeah, great. So it turns out for some kinds of constraints, you actually can do this.
Yeah.
Like for unique game constraints, you can do this, but in general, you can't. So to recap, we test for rigidity, then we're going to check the constraints, but there's this other cheating possibility, which is you're sending me inconsistent assignments. because I'm sending the whole list of variables. Good. So the goal here is to construct some set of unitaries, U1 to UD, such that if you're honest, if you have a consistent assignment, then psi is invariant. But if you're inconsistent in some way, then psi is not it's kind of detectably far from UK on psi for some k. Okay, so suppose we have these unitaries, and I'll tell you how to just construct them afterwards. If we have these unitaries, then what we do is you'd choose a random k from 1 to d, and then we'd run the Hadamard test on psi and UK on psi. You can think of the Hadamard test like a swap test, but we're kind of controlling on the unitary. So this is what we're going to do, but I haven't told you how we're going to make these unitaries. So how do you make those unitaries? Sorry, go ahead. Swap identical variables.
Well, appearing in two different classes, you could just swap.
Yeah, this is the right idea. Yeah, good. Okay, so we're going to basically build a graph. We're going to build a graph using the preprocessing step of Dunar's proof of the PCP theorem. But we're going to turn each variable into a cluster. We're going to turn every variable into a set of vertices, one vertex per constraint. And then once we have the cluster, we're going to add an expander graph within the cluster. So I'll give you an illustration of how this works. So here we have, let's say, one variable I is in black, and it's attached to 5 constraints. It's involved in 5 constraints. We're going to create 5 vertices. They're in orange. And then we're going to add an expander graph that's in green. So we're going to do this for all variables. So G is going to be the union of n different expander graphs. But note that it has R times Q vertices. R is the number of constraints, and Q is the uniformity. So we're going to create this graph. So recall that this rigid state is of the form like this. We're uniform over the constraints, and we have the variable list of the involved variables. The values of those variables. It's going to be convenient to separate the variables out. And what we would like is kind of to have every variable assignment on its own, on its own. So maybe uniform over the constraints, uniform over the indexes of the constraints, and then kind of like each entry of the variable. Because now if you look at this, now we have R times Q, options in the first register. And we have kind of one option for each vertex of this graph. And I'll just say one thing, that this map from going from psi to phi, we can actually do this. There's a little bit of it's a little tricky, but I'm happy to talk more about it offline. So suppose now we have this phi, this kind of uniform over the superposition, uniform over the vertices of the graph with some variable assignment according to that value. What we're going to do is we're going to decompose this graph into permutations. We can take a deregular graph, compose it into d permutations. So if we had this deregular graph where d is 2, you can kind of take the half edges and draw 2 different permutations. And what we'll do is we'll set the unitary to be kind of the action of this permutation over that first part, over the j and the index of the constraint, of the variable involved in j. And kind of now that we've done this, the key idea is that if you have an honest assignment, all the vertices are only connecting variables. So if you have an honest assignment, or a consistent one, then the value shouldn't change as you go from one part of the variable to another part of the variable. So if you stay within the cluster, the value should be the same, so you're kind of invariant. And this expansion property, the fact that we use expander graphs, kind of amplifies the cheating. That's like the intuitive picture. So the protocol is this is the protocol. We test for rigidity, we check the constraints, and we make sure the assignments are consistent. Questions?
one assignment that's off, how far off are you in this map of UK, right? UK then doesn't map side to side, right?
Yeah. So it'll scale with the amount that you're off. It'll, like, if you're off by just one value, you're not going to catch that so much. But if you're off by a lot of values, if you're far from kind of being consistent, then you'll fail with some concept.
And what is and how does this expansion property help you in that job? Right? Like
Yeah, so it's kind of the way I think about it, the qualitative way I think about it is that what expansion is doing is it's kind of, you can't just, be cheating on a few variables that are kind of far away from the rest of the graph. So if you cheat on a few parts of this cluster, it's super connected to the rest of the cluster. And so you're going to find it in these other edges that you've been cheating. So it kind of amplifies the fact that you've been cheating.
Yeah, so I guess my question was how much, so I was imagining an area where you're just, there's one place where it's different, so that should get amplified, right?
Yeah, it'll get amplified by a factor, let's say 2 or something like that. It doesn't need to be a very good expander, just some constant expansion.
I'm missing. Maybe there might be two notions of expansion being used. One is the expander here. The second one is the expander inherent in the PCP. You started off with a PCP version of the CSP, right?
I see.
So can you clarify in this last comment which expansion you're talking about there?
I see. Good. Thanks. So this expansion I'm talking about is in this last part, this consistency test, where I built this new graph. So this is after I've already PCP'd the problem. So my input now is this already PCP'd problem that has a completeness 1, soundness 1/2. And now eventually I'm going to build this graph that I'm going to add kind of another set of expander graphs in it.
My confusion, I guess, here is Q is supposed to be a constant, right?
That's right.
So even if you just pick the cycle, like the spectral gap of a cycle is like it'll be like 1 over Q squared versus this. So I don't really see where the expansion here is.
Yeah, that's a good question. So I should say that the size of the cluster, we don't actually know what the size of the cluster is. It could be polynomially large or in NX exponentially large. The size of the cluster is the number of constraints a variable is involved in. And so it may not be a constant.
Confused. The optical instance where that's true.
Because you do the same cloud thing.
Mm-hmm. I think it's possible. So the reason you need something like consistency is because you need a way to check the constraint and to make sure you're not, cheating in consistency at the same time. And so the way that I'm asking for the quantum state is I'm asking for each constraint and the values going with it. I guess if I was asking something else, then I wouldn't need to do this. So I guess it's like a PCP in the PCP, but this is what we need to do to get the right, to get a constant gap. Yeah.
Can you remind us in the proof of the PCP that you proved, what the pre-processing steps to change?
Mm-hmm. So, the part that we need is this amplification of cheating. So what this does is now that we have expander graphs everywhere, it kind of does a couple things. One, now the graph is regular. So that's really important. Now that the graph is regular, we can work with it with, let's say, a constant, D regular, D is some constant. But the expansion also helps with cheating that kind of, either you've been cheating on the constraints, the original constraints, which are hyper edges, kind of in this model, or you're cheating on the expander edges. So this is actually, you're right, this is kind of how we get a regular graph from a, not necessarily a regular CSP. Okay.
So in the QMA case, this is simplified because they have two copies and they can do some other tests?
Yeah, that's a good question. So in QMA 2+, in that paper, they actually do need this for the NX part.
Okay.
For the NP part, they study a different problem. They study a problem that's a unique game problem.
Okay.
And in the unique game problem, you can do something as Umesh suggested, which is like you only list a variable and its value.
Okay.
And you can still check the constraints. The problem is now when you scale to NX, there's not a strong enough PCP known for NX that is also a unique game So they switch back to this general CSP, and then they have to do something like this. So this technique, yeah, by the way, this technique is used by Deneur, but also used by Jeronimo and Wu. Great. Okay, I'll just say a few words about how do you scale this up to NX. The reason I present it in this way as opposed to talking about unique games is because now the only thing we have to do is worry about succinctness. So okay, so we need an NX part problem now. So we're going to have capital N be 2 to the little n. And the instance now has to be succinct. There has to be, let's say, a poly-size circuit that represents the instance. And the question, is this instance fully satisfiable or not? So again, by the PCP theorem, so even for constant size alphabet and constant uniformity, we can still get a constant gap. Either we satisfy all the constraints or only half of them. And so the plan now is we're going to put this in QMA plus with a polynomially sized proof. So I will say that the NP protocol just almost works. The main thing we need to do is we need to ensure that Arthur's protocol is efficient. And the only issues come up in this consistency test. In particular, there's kind of 3 big issues. The expanders could be exponentially large. That's because a variable could be involved in exponentially many constraints. There could be exponentially many expanders because those degrees could be of different sizes. And the adjacency list could also be exponentially large. So kind of the problem is all about just representing the CSP instance and being able to traverse the CSP instance.
It's NXP, right? The CSP is exponentially big? Or?
Yes, that's correct.
Okay.
Yeah. So now we've moved to an NX hard problem. So we have exponentially many constraints, exponentially many variables. And so there are solutions for these, which Jeronimo and Wu also address. For exponentially large expanders, we can construct them in polylog size of the graph. We can also decompose them into permutations in polylog size of the graph. For exponentially many expanders, we can use kind of the strongly uniform PCP. So a PCP where the number of constraints a variable is involved in is one of constantly many options. So now we only have to draw constantly many expanders. And the third question about adjacency lists being exponentially large, we can also use a doubly explicit PCP. And this kind of strong property of the PCP allows us to traverse the variable indices and variables and constraints in polylog size of the graph time. So once you do that, everything else works. These are the only adjustments you have to make. So I think I'll leave you with a couple of conclusions that we came from this work. And the first thing is that these promise symmetric classes are really powerful. They can, both this QMA2+ and QMA+ can reach NX. But the promise gap seems to really matter. Like in QMA+ in particular, in constants, you can get from QMA to NX. And like one question you could ask is like, what are the right constants? Are there constants that give you kind of like a phase transition? Like, is there a constant where it's contains X? Is that a different constant than NX? And so on and so forth. We don't know any of these. We don't know any of these.
Is there a transition if you move the plus? You can also interpret from the plus to a non-plus by only
Yeah. So right.
There should
So
be 99% weight on positive.
right. You can ask for weaker conditions than plus. Like, is there, if you add some complex phases, how much complex phase can you have? Yeah.
Is anything wrong?
No, not that I know.
Do we know that QMA with real amplitudes is equivalent to QMA with complex amplitudes?
Yes. It was in the Cake paper.
Yeah, good.
The second thing is really back to the story of QMA2, which is, this QMA2+ was invented to study QMA2. And suppose you still want to use this positivity to study QMA2, but just know that any technique that's going to amplify the promise gap can't work for QMA1+. And so you're going to have to be clever about using unentanglement and positive amplitudes together. It just presents a new challenge in this direction. kind of, the big question is, what is special about QMA 2 plus that QMA plus doesn't have? What does it have that QMA plus doesn't have? And, if at all. So thanks.
Questions for Kunal?
Just coming back to this question about whether you can allow a few negatives, right? So it looks like the way the positivity is being used is to make sure that the superposition is well spread out by the looking at it in the Hardeman basis. But if you do that for a general state, you would let's say we only had real amplitudes, but then you'd be checking if the all zeros coefficient would be either highly positive or highly negative, but now if you're told that you have very few negative entries, wouldn't that give you almost everything you need?
I think the rigidity will be the problem, right? Because there's where you're having minus to still help.
He was talking about rigidity.
Okay. Oh.
Yeah, it's possible this works. Yeah. So I think the core of the question is like how strong is this plus promise? Can you weaken this plus promise? And maybe it's either too strong or not there. I'm not sure.
Okay, if there are no more questions, we resume at 3:30.